Hey, okay. On example 2, in lesson 4.2, it says at t equals 0, determine whether the particle is moving to the right or left. And they gave you a table of values with the time and the velocity and particle moving along the horizontal axis. So left and right. All right, well, okay. When we look here at t equals 0, we see the velocity is negative. So at that moment, the particle has to be moving to the left because a negative velocity indicates a movement to the left. All right, and that's exactly what we need to say. All right, so t equals 0, particle is moving to the left because the, the velocity at that moment is 0. Oh, is negative, sorry. Go down on your topic. Okay, is there any time between 0 and 15 when the particle's at rest? Okay, well, it says up here that this is a twice differentiable function, which means that the derivative, first derivative and the second derivative are both continuous functions, okay? That's what that means. So in other words, it's a smooth curve. It's not jumping around, it's traveling. So we went from -4 to -1, and then we went to 1. So we are, because it's differentiable and continuous, because of that, we know that in between here, the velocity had to be 0. Now, could it have been 0 some other time? Could it have gone 3 to 0 into 5? Yeah, who knows? But we aren't guaranteed that on that interval. We're guaranteed it between 0 and 2, 2 and 3, because there's a 0 in between -1 and 1. That's called the intermediate value theorem, okay? All right, so I would say, since the velocity function is continuous, the intermediate value theorem, okay, guarantees a value of 0 for the velocity struggling on the open interval 2 to 3. Okay. Now, you wouldn't have to say the open interval part since I wrote between 2 and 3, or you could just write that out in words. Between time equals 2 to time equals 3, we're guaranteed to have a 0 because the velocity went from negative to positive on that interval. Okay. Yeah. Yeah, I think that's all that we need to say. Okay. Then on the next one, use the data from the table to find an approximation for v prime of 8, or the acceleration at 8. All right, and so that's what that next part's talking about. Explain the meaning in terms of the particle motion. So we're approximating the acceleration and indicate units of measure. Ah, perfect. Okay. Well, 8, is in between these two. So, typically they'll put it exactly in between. But that's okay. We can still use those 2 points right there to approximate what we think the velocity would be at 8. Okay. Normally they'll have it centered, but in this case she did not. That's okay. So we'll just say the velocity derivative. So the velocity derivative of that at 8. We don't have that any way of calculating that. We don't have an equation or anything like that to take the derivative of, but we can say that this would approximately be equal to, okay, and what they use, 7 and 10. So the slope between 7 and 10. So I'm going to say v of 10 is y2 y1. And then here comes x2 and x1. Okay. And that value is, we got to go back up and look at the table. V of 10 was 5. And V of 7 was 3. So I got 5 minus 3 on top. So 5 minus 3 on top. And on bottom, I have 10 minus 7, which is 3. Okay. So this is going to be 2 thirds. And the unit of measure. All right. So up here, we're talking about feet per second. So this is the acceleration we're talking about. So this will be 2 thirds feet per second squared. Feet per second per second. Okay. And the meaning of it, we haven't said that. Well, we said it, but we haven't typed it out. So V prime of 8 is the acceleration of the particle when t equals 8. Okay. All right. We got a couple more here. We'll stop there on this one.